Thank you very much for attending here. My talk is about fuzzing for worms, or about, in other words, about AFL for Linux network servers. So, is this working? Yes, somehow. No. Murphy's Law. So I'm Dobin Rutishauser. Fuck. Desynced. Sorry, I will fix this quickly. Okay. My name is Dobin Rutishauser. I work at Compass Security. I gave several talks previously, but on a smaller size of audience. I'm also a lecturer at the Berner Fachhochschule. Some students are here, very good. They followed my call. So I will be talking about fuzzing. First, what we currently have, which is basically mostly file-based fuzzers. Then a bit what I wanted, and this is a network fuzzer. I will try to make a live demo. I will talk a little bit about feedback-driven fuzzing and discuss the results afterwards. So who knows about AFL, American Fuzzy Lob? It's about 1/3, very good. So on the left you see here, that's how you set up American Fuzzy Lob, AFL. It's a file fuzzer. Here we are fuzzing bin utils, or to be precise, redelf. So all you have to do is have the source code of the application you want to fuzz, compile it with the AFL compiler, then give an example file. This is here in the example in the AFL in directory, and then start fuzzing. So AFL is probably the most known fuzzer and most widely used in the previous few years. And I think this is mostly because it is very easy to use. So everyone can start very quickly, and it's giving useful feedback if you did something wrong, if you have some wrong settings or configured it not correctly. It's also very fast. It's usually about like 2,000 iterations per second. And it also has code coverage feedback, which I will be talking about later. So AFL is out since several years right now, and everything is basically already fuzzed. We have all the JPEG file parsing libraries, we have SQLite, we have even some network servers, we have TCP dump and Wireshark, and we have like 1,000 different other tools where AFL found vulnerabilities. So I thought, sad Pepe, everything is already fuzzed. Isn't there something which is maybe possible to which is not fuzzed already so much? So then I light my eyes on fuzzing network servers. This seemed to be a nice little niche where it's not so much development already. So when I mean fuzzing network servers, then I mean fuzzing the data layer. So I'm not fuzzing TCP or IP or Ethernet or whatever, but really application data. One example is MQTT protocol. I intentionally took this example, why you will see later. MQTT is often used in IoT frameworks and IoT devices. It's basically just a publish-subscribe protocol. So you can like subscribe to a temperature channel, and the devices push the temperature, and then you receive it. This MQTT protocol has like 3 basic messages. One is connect. This is the first packet sent to the server, more or less with the name of the client. Then you can subscribe to a channel, and you can publish a message to a channel, which is pretty simple and easy. So So basically the MQTT server has a state machine and it's looking for packets, and if it receives the connect packet, he knows, now in the state connected, he's receiving another packet, maybe subscribed, and he's handling this, and we want to fuzz this MQTT server. What possibilities do we have to perform this fuzzing? I invented two words for this, or two methods. The first method I call wrap, and the second method I call rewire. And I will talk very quickly about these two methods. So the first method, the wrapping, is basically just to isolate the functionality which is performing the parsing of the MQTT packet in this case. But usually this comes from file parsing. Maybe we have a function in Word or whatever called scan docx file for viruses, and then this function we are able to fuzz and only this part and ignore all the rest of the application. This is how it is done in libfuzzer and WinRFL, and also in AFL persistent mode. This is usually very, very fast. To discuss a bit the problems, as you can see, I wrote here parse MQTT packet. Of course, this doesn't exist in the actual Mongoose server. It's way, way more complicated, and it's not isolated function like this, but it also generates answers, tries to set up networking. So this was not really applicable when I wanted to fuzz Mongoose MQTT server. So the second method I call rewiring, and this comes from the fact that in Unix, network socket is basically just a socket. Here it has the number 4, so it's just an integer. And the program reads and writes to this socket, and the packets go out and arrive at the client socket. So it's easy to see that you can just replace this network socket with a file socket. Because then we are able to use AFL again. Just write all the network packets into a file and tell the MQTT server, hey, no, you are not reading now from the network, but from this file. There's a library which helps doing this called Preeny, which has a DSOC capability. I tried this library at Mongoose 6.8 and it didn't work for hours and hours, so I was getting angry. And I made it manually, and I made rewiring basically, so that the Mongoose is reading from a file and not from the network sockets. I fuzzed it with AFL and also got very quickly a stack-based buffer overflow. Fun fact, I finished the exploit for this on my flight to DEF CON in this 10 hours. It was a bit more complicated than I thought. It was like a buffer underflow. But what I realized here is that it took several hours of patching and debugging until I had Mongoose that it was fuzzable. So I wanted to make this a little bit easier. Other problems, as maybe some of you already thought about when looking at my slides, is that if we just write the packets into a file and mutate the file, the fuzzer has no idea where the packet delimiters are or what are the different packets. So it will just look at it as a file, like a JPEG file, for example, and mutate it. Basically flip bits and looking if the target is crashed. The target server will also read these packets and maybe send an answer, but this answer is going nowhere. The fuzzer, like AFL, doesn't read from the file. It doesn't have a concept of this. And this can or cannot, or can be a problem, but doesn't necessarily need to be. So this is like a suboptimal solution to use a file-based fuzzer to fuzz a network server. Is there a better way? And Jein, yes and no. There's another type of fuzzer called generational fuzzer. Basically, you specify the protocol you want to fuzz in an XML or something similar, byte for byte, then what does the first packet contains, what does the second packet contain, how does it look like, and once you specify the protocol, in this case FTP, then the fuzzer will smartly generate invalid packet, but still more or less according to the specification. There are several of these fuzzers. Probably the most famous is SpeechFuzz. They also made a company around it and implementing all these protocols. They call it XML PITs. So they implemented FTP and email and web and probably pretty much everything, even MQTT. But you have to pay for it. There's also BooFuzz, which is based on Sully, which is again based on Spike, where you define the protocol in Python, more or less, and you have tools like NetsOB or Pulsar, which should assist you with this reversing and re-implementing the protocol. But I wanted to fuzz, for example, MQTT, but I haven't found any implementation freely available which I could use one of these fuzzers. Then I wanted to fuzz an IRC server, and it's the same, like there is no central repository of this protocol specification, which I can freely use to do my own fuzzing. So this was about generators, and I realized one important distinction about network protocols is that you can split them into stateless and stateful protocols. The stateless protocols, which are surprisingly many, like DNS, DHCP, and HTTP, you basically just send a packet to the server, he answers you and forgets you completely. Every request is completely independent of the previous one, mostly. I think these stateless protocols can be fuzzed pretty good with a file-based fuzzer, because you put the HTTP request into a file, fuzz it, send it to the server, and do it again until the server crashes. But there are also stateful protocols, like the example was MQTT or TeamSpeak or whatever, where there is a TCP connection with several packets depending on each other. Like the TCP session is kind of like a session. So for the stateless protocols, before I created Fuzzing for Worms, you could use AFL, and for the stateful protocols, Peach was basically the best way to fuzz it. But I'm very lazy. I don't want to patch network servers. I don't want to XML protocols. I just want to perform some fuzzing. How hard can it be? So last year, I think after DevCon, I started to implement FFV, Fuzzing for Worms, and basically to apply the AFL approach of mutating packets into network services. So what are the steps of FFV? First, I intercept some package. It's basically like providing an example file, like a PDF file, if you want to fuzz Acrobat with AFL. Then I replay the data which I intercepted with some modifications, the actual fuzzing. I detect crashes in the server, and at the end maybe make some money with 0 days or CVs or whatever. So I make the first demo, praise the demo gods, and I will reproduce the Mongoose MQTT 6.8 vulnerability. So the Mongoose source code I downloaded into Mongoose and checked out the correct version. I compiled the example server of Mongoose MQTT broker, that one, and copied into the binary directory. I also have a configuration file for Fuzzing for Worms, which basically just specifies, let's make it a bit bigger, where the target is, the binary name, and how I give the target port and what is the default port. Then let's intercept some packets. So I start the interceptor. It's now listening on port 10,000 and forwards all the packets to the destination server. I downloaded this cute little MQTT client, already prepared the connection. So me as a security analyst, I have no idea about MQTT, just know it's a bit publish subscribe. So let's subscribe to the topic area 41 and maybe publish something there, test. So this appears to look good. Send some example messages. Fine for me. And FFV now stores these packets in a pickle file. Genau. So this is basically just, could also save it in JSON, just the data which was transmitted. So here's the MQTT connect packet with my name. Here is the subscribe request, and the server answers something like, yeah, you are now subscribed. And I was like posting test to this topic. So it looks reasonable. Then one important step, not here, but usually is to test this recorded data. So now I replayed this data 32 times, and it worked all the time. So this looks like ready for fuzzing. And I start this like this. So after a few seconds, we already identified some crashes. This vulnerability is in the length field of the MQTT packet. If it's below 2, then it's a buffer underflow, and I think it mostly detects this vulnerability. So I'm fuzzing here with 2 threads, about 4 iterations per second. All the crashes, or the data which generated the crashes, is stored in the directory crashes, as you can see here, and it's basically the same data structure. So it's the data which we recorded, and somewhere we did some fuzzing. Yeah, this is the message too. So FFV modified something on this message, and this should have led to a crash. Sadly, Mongoose is very unreliable. It stops accepting connections after like 20 connections. So I restarted like every 10 connections, but then it detects a crash every 10 connections, because when you kill it, then the address sanitizer will detect that the buffer is not freed. So we are lucky. The first one is a crash, and the others not really. And let's start this. The server in GDB, and we play the file which generated the crash. So this was the 1505. So, and we see in the GDB, it really generated a crash, obviously, because I verified it. So now we have the 0 day, which is not again 0 day because they patched it in Mongoose 6.9. If that is looking quite unimpressive, I basically achieved my goal. It should be very easy and without much trouble to find vulnerabilities in network servers. So the FFV has several stages. The first you have seen, we intercept the network data. It's also possible to just capture it with like TCP dump and convert the PCAP to the pickle file, but usually I just intercept it on the fly. We test it, if this intercepted stuff really works, we fuzz it a bit, we verify, so we remove the false positives. Then at the end we minimize it, because if you have 10,000 crashes, then you want to know the unique ones. And at the end I wrote the web GUI, maybe I can show it, which is now a bit work in progress, where you can browse all the crashes, which can be quite large, and have all the data, and to start writing an exploit if you have enough time. Sorry. So here we have the normal client, our graphical MQTT client. This was thinking it communicates with the server, but it was communicating with Fuzzing for Worms, and it wrote all the data into a file. And then afterwards we imitate the client, we read the file, read all the packets, select one of the client packets, and mutate a little bit, and then send it all to the server, which means we create a TCP connection, send the first packet, read the answer, send the second packet, read the answer until it's finished, and then we do it again with another mutation. Maybe some of you guys are asking, how is this like mutation performed? And I can say I don't care very much, I'm just using Radamsa. Everyone is using Radamsa. Radamsa is what many understand as a fuzzer. It takes some data and it mutates it, and then we have some different data. And it's very smart. It detects like XML and other file formats, and it's doing smart stuff. So it was not necessary to develop something for my own. Just use Radamsa like everyone. One interestingly hard problem was to detect the crashes. So if we send a smartly fuzzed packet to the server, which makes it crash, and then ask the process, hey, are you alive? Then it was always saying, yeah, I'm alive, instead of being dead. I think in Linux you have some kind of lag or latency until the process is really identified as crashed, which was very annoying at the beginning. So I thought of a much smarter way to identify crashes, and it's basically just if I cannot connect to the server, he's probably crashed. And if I cannot connect at the TCP handshake, the fast data, the previous iteration probably caused the crash. And if it's crashing after or when I send the mutated packet, and it's probably because of this packet. So this was quite an important distinction to be made. Afterwards, if the server is crashed, I want some information. It's not very useful just to have like 10,000 network data replays which make the server crash, but you also have to have some information. I collected a lot of information, but basically what you really need is the stack trace to know which function, at which line it crashed, and what were the previous functions. So this is also useful then to make the minimization of all the crashes. First, I used the Python ptrace library. This was awful. It didn't work. It crashed. It had bad backtraces. So then I created a parser for the address sanitizer log files. Basically, address sanitizer doesn't really sanitize addresses, but adds code so you can identify heap-based buffer overflows and stuff like this. Like you've seen before in GDB, it makes beautiful output where exactly the overflow happened. But this was not for stack buffer overflows. So now I'm starting in the verify phase. I start the server in GDB and replay the network data which made it crash, and then parse the output of GDB and try to extract the stack trace. So the previous stuff, the man-in-the-middle stuff, the sending and mutating data was very simple. It was like done in 4 days. But like the trouble was in developing fuzzing for worms more in other areas, like this stack trace parsing or restarting of the server or identifying is the server really crashed or not. I like hardware, so I bought myself some CPU power to fuzz a bit more professionally. Xeon E5 from 2012. It has like 8 cores, so with a hyper-threading 16 threads and in parallel and 32 gigs of RAM. And this double, so you have one here and one here. So you have like 40 megs of cache and 64 gigs of RAM. And all this with the CPU coolers and power supply and the RAM, it was like $700. It was awesome. So I just needed the case and the SSD. But sadly, what I really needed was more something like this. If there are really vulnerabilities in the network servers I tested, I identified them very quickly, like after half a minute or a minute. So all this power was not really necessary. But my server was fuzzing. It heated up my office. But somehow I thought, this is not very smart. I'm not a step closer to a fully automatic AI which hacks other people or something like this. It's just mutating, completely dump the network traffic, look if the server is crashed, and then does it again. But maybe we could make it smarter. And we can make it smarter, especially with this technique, with feedback-driven fuzzing. What we want, basically, that if we identify, like we fuzz something, we change some values, maybe making the number 1 to a number 2, and suddenly we find new functionality. We want to store this corpus, which led to here, x2. So then we can use it as a basis to continue our fuzzing. Maybe find bugs much deeper into the program and explore all the possible states, or a large amount of the possible states. And the normal fuzzer, a dump fuzzer, just mutates it and maybe it randomly reaches this location, but it's all by accident. Usually we don't not only want to do this on function level, but on basic block level. So basic block is what you always see in IDA. Once entered in a basic block, the execution will continue until the end. And then it's again changing to a new basic block, as you can see here. So all the control flow is between the basic blocks. And every function consists of at least one basic block, so we can use this to really explore the whole state of a target server. For example, here we have a comparison. We have a crash if the input is ABCD. And This was more or less made popular by AFL. You have this Bloom filter here. And if you use AFL GCC, the AFL compiler, the compiler will add like 3 lines of code after each basic block, which will update one value in this Bloom filter. So if we reach this basic block, it will increment this number here. We fuzz some more. Maybe now the input at the second place is now B. Then it changes this bit, or byte to be more precise. And the fuzzer will always send some data to the target program and compare this Bloom filter with the previous one. And if there's one little difference, one more number 1, then it knows the input called a new function, a new basic block in the target. And with this, instead of like brute forcing a value of 32 bits, which is 4 billion possibilities, you can just have to guess 4 times 1 byte. So it's just like 1,000 possibilities. So it's much more efficient to search through the space with the feedback-driven fuzzing. This will look like this at the end in the source code. I think this was generated with lcov and gcov, but it's basically the same. Once you have these different corpuses exercising different functionality of the program, you can resend all of them and then paint your source code, like which ifs and which elses have been reached by the fuzzer and which one not, and then improve the fuzzer or the fuzzing technique. This method is surprisingly efficient. So it was a test with AFL, JPEG parser has been fuzzed with just writing hello into a file. So it's basically just an invalid JPEG file. Let AFL run for some time, and step by step it like reverse engineered the JPEG specifications, and it generated more or less valid images just by brute forcing it through the search space of the JPEG parser, which I think is pretty cool. So I wanted to have this for fuzzing for worms, and I was Googling a little bit what is available, and I found this page here from HonkFuzz, where it was a little bit some explanation what different functionality you have nowadays to perform this code coverage feedback. Hardware, you can use hardware like Intel BTS and Intel PT. Intel PT is the newer one. I think it's available since more or less Skylake and used in KAFL to fuzz operating systems, but also all the current compilers like GCC and Clang already have the support to add this code coverage mechanism into the code. So I was inspired a little bit by HonkFuzz. I started to, I think I randomly selected one of these, tried to implement it by myself, and copied more and more code of HonkFuzz into fuzzing for worms, until I realized even if I, after weeks or whatever, made it to work, still like HonkFuzz from Google is has like all these cool code coverage techniques, and I'm always lagging behind. Why am I not using HonkFuzz itself? By the way, is Robert's wiki here? The author of HonkFuzz? Okay. Anyway, so basically I instrumentalized HonkFuzz, that it's not really fuzzing, but just using it as an oracle for code coverage. So HonkFuzz will observe the target FFV will communicate with HONKFOSS via Unix domain socket, and it will also send the networked data directly to the target. Very too slow or too fast. So then it's a simple protocol. HONKFOSS will tell Fuzzing for Worms, hey, please do some fuzzing. Fuzzing for Worms will send mutated data to the target, and HONKFOSS will either say, then we say, yeah, we send our shit to the target, our TCP data, and then HONKFOSS will say, yeah, you reached the new basic block, and then Fuzzing for Worms will add what it sent to the corpus. Or it says, yeah, the target is crashed, and it's very good, we handle this, or most of the time nothing happens, and just saying again, please fuzz some more. So this is my second demo. Oh. So they patched my vulnerability in Mongoose 6.9 and was thinking maybe there are some more vulnerabilities. And of course there are. I already prepared everything. So basically you can just start FFV with honk mode parameter. I have here 2 threads. It starts with 2 corpus files, and already in a few seconds I generated 16 other corpuses which are depending on other on 2 parents. And it's quite interesting to see. Yeah, maybe make this one big. So all the corpuses, all the newly generated files are stored in a file system, and you can see how it's advancing. So here it first the second message found a new basic block, then first based on that one, the first message found a new basic block, and so it's going deeper and deeper and finding more and more functionality of this MQTT server until I reach the file name limit of Linux. I think it's about 255 characters. I have to speed up a little bit. The most important part, how performant is this thing? And it's not very fast. It's about 30 iterations per thread. So this includes reading the stored corpus, selecting a message, mutate it with Radamsa, then create a TCP connection, send all the packets, read all the answers, and then its next iteration. So on AFL, it's usually recommended to use half your core count as active threads. On FFV, it's basically the server is just most of the time setting up and probably tearing down TCP connections. So it's waiting all the time. So you can use core count multiplied by 2. With my machine, it's about 2,000 iterations per second, which is about as much as AFL single threaded. So it's kind of okay. But just having, at the beginning I had this 30 iterations per second, which was very bad, so I had to have multiple fuzzing processes. This also generated a surprisingly large problem, because you have to tell the server, hey, every server needs to listen to on another port. Not all MQTT servers can listen on port 1883. So some servers use it via command line. Then you have servers which have configuration files like IRC servers. Then you just prepare like 100 configuration files with different ports and then give this as specifications in the command line. But all this was very bad. And I stole an idea, brilliant idea of also HONKFOSS, and it's Linux network namespaces. As everyone knows, network namespaces is also used in like LXC and LXD and Docker and all that stuff. It simulates a new, completely independent network interface for a certain amount of processes. Like you can say, from now on, I want to have a new network namespace, then you have your own loopback device, and then you can, without having any configuration changes on the server, to have arbitrarily many servers fuzzing in parallel without them killing each other. So we have the master process communicating with a queue to the slave, which is communicating with a Unix domain socket to HonkFuzz, which is via shared memory getting this code coverage of the server. I send TCP data to the server and then send basically just statistics back to the master. All slaves observe the corpus directory. So if one of the slaves find a new input which exercises new basic blocks, it just stores it in the directory. All the others get notified via iNotify, and they add it to their corpus, and everyone always have all the possible states, which is pretty cool. So that is how it was working. Fuzzer is only as good as it can produce results. So I tested it a little bit. I was a bit more developing than testing. So there are not so many results. But of course I found the initial bug in Mongoose MQTT 6.8 and then in 6.9. I found in libcope and all these nice IoT libraries, and usually found the bugs pretty fast. They're all available in a Docker image, and I didn't have time to notify the maintainers. So if somebody wants to have some free CVEs, can download the Docker image, do some fuzzing, and get famous. Interestingly, like the Mongoose Web DNS and DHCP protocols, just fuzzed it for like half an hour, but it was no bugs, and I think it's also because these are like simple protocols and easy to test, so without state. Maybe someone tested it already with AFL. I tried Synergy. This was awful. It didn't work at all, as expected, and surprisingly, all the IRC servers, I also haven't detected a crash. Here's some more statistics. So I had a bug. I let it run with 8 threads, but every thread just executed 1 iteration per second. So we have here 8 iterations per second. But we still see on the bottom, like these are the amount of basic blocks, of the unique basic blocks we identified, and it's growing slowly but steadily over a week. So I think this was like 1 week. This is from AFL plot. I made the output of FFV compatible, so I can also make fancy, nice graphs. Oh yes, this was the server Inspire IRCD. I fuzzed another IRC server, NG IRCD. Here it was working more properly. It's surprising that it gets slower at the beginning. Whatever, it was about 120 iterations per second, and also here I reached after 2 days about 2,500 basic blocks. So it's really crunching through the search space of the IRC server. So the conclusion, fuzzing for worms, it can intercept network data. It will retransmit it with a little bit of fuzzing, and it's detecting crashes and new basic blocks. The motivation was like, or as I've seen now, it's way too slow to do some really serious fuzzing. You want to have performance like AFL with like 10 or 20,000 iterations per second, which is like 100 times faster than fuzzing for worms. So you find bugs 100 times quicker. But this will always need some modification of the target server, some code modification, debugging and reverse engineering. So I think fuzzing for worms is useful at the beginning. Just intercept some data, start to fuzz. It's set up in like 10 minutes. And in the 4 hours which you need to patch the target to make it AFL compatible, maybe fuzzing for worms already found some bugs and you're writing CVs instead of patching servers. As Chris Bisnet said, always be fuzzing. So if, like what I previously said, should not have wasted time, always be something to fuzz. Maybe you find some bugs, maybe not. And even if it's just a stupid dumb fuzzer, maybe it gets lucky and finds something. So the code is on GitHub. I'm on Twitter. I write a little bit about some problems in my blog. I also have the Docker container, which you can download. And I'm also on Reddit on Fuzzing, which is, has all the new fuzzing technologies, but not much discussion. So come and say hi. And I think I'm perfectly in time, surprisingly, and available for questions.
Beautiful. Hey, thank you very much. Gotta love the Swiss efficiency on that. Yeah, so we have a final few minutes, I think, available for a bit of questions. So does anyone have any questions that we would like to have? I know it's the last session. I know our brains are probably dead and full of info. Anyone, anything? No? Oh, letting you off easy. There you are. Last talk and
Perfect.
You get it easy. Great.
You can talk with me afterwards. Just find me.
Awesome. Okay, cool. Hey guys, thank you very much. I guess that concludes all the talks for this year's con, so thank you very much. We still have a final closing ceremony happening in around 10 minutes now, so please don't go away just yet. You can take a little break now, grab a refreshment, and then we should meet back here in around 10 minutes for 4 o'clock for the closing ceremony. Thank you.